Hello, everybody. This is Dr. Bachnight coming at you, and this is our first lecture for um, the class. So every week or every Tuesday and Thursday, I will try to post a new lecture about what we're going over in the chapters. And today we're going to go over chapter one. All right. So let's get started here. So this is the way your book should look. So hopefully everybody got this is available at the bookstore or online. You don't need the a compliment little package that comes with it. Everything else is just going to be online. But it is helpful to have this book to help you do those chapter reviews and everything else. So I'd highly advise getting it on your bookshelf there. Okay. So in this lecture, we're going to help you understand the field of environmental science. We'll talk about the importance of natural resources and ecosystems. We'll talk about population growth, resource consumption, and the humanity's consequences of that. We'll talk about the ecological footprint, scientific method, the difference between ethics, what ethics are, global environmental pressures out there, and we'll talk about the concepts of sustainability and sustainable development. And this is how we're going to really handle this course. Is we're going to talk about it in the sustainability and the sustainable development concept. All right, that's what I like to live by, sort of, and we're going to understand these two things much better by the time we're done with this class. All right, so the quote for this chapter is David Orr's quote: "When we heal the earth, we will heal ourselves." And I firmly, firmly believe this. And, climate change is a big issue in my life. And I firmly believe that if the world just starts acting a little bit more cooperative and starts to try to work together so we can change our carbon emissions into the atmosphere and messing up the carbon cycle as we're doing, which we'll learn about later on. And we all work together. All these problems we have out there in the world, a lot of them will just kind of dissipate. A lot of the war and the poverty and famine and disputes going on in the world. I think a lot of that stuff would just, we would heal us as a society as well. Not to say that our society is too bad, all right? But I think some of those problems are kind of exacerbated from climate change. So if I think, if we get together on a global scale, because that's the only way it's going to work. We can't just do it by the United States does their thing and then China does their thing. It doesn't work like that. We got to work together as a whole community. So, I really love this quote. And I think about it often. That if we got together, we would heal a lot of these problems that we have. And we've seen that happen in the past, too, as we'll point out later in this class. So environmental science also means jobs, jobs, jobs for you. All right. A lot of people don't think, environmental science is just one of those electives we have to take for a science class to get through. But there's actually everything's connected. All right. I mean, the most common jobs you have is, to be a college professor or an environmental scientist or a high school teacher. But believe it or not, environmental science is connected to a lot of things. So there's now a huge industry for environmental reporters. One internet YouTube kind of thing I listen to for my news. Just hired a full-time climate reporter. Right. Environmental science also deals with toxicology. All right, so you can find out what kind of pollutants are in the water and things like that. And also, the big law, environmental law. Was it Aaron Brockovich movie? Right. She wasn't even a lawyer, and she got into it. Right. There's also some specialized jobs in forestry. You can actually, want to transfer to WVU, you can get a master's. Well, State Rock Morris for your undergrad and go to WVU for your master's in forestry. All right. There's also environmental engineers out there trying to get rid of our sewage and all that other stuff. And there's also a consultant. So there's a big industry in environmental consulting as well, because every building that gets built around the world has to have what's called a environmental plan. All right, and they got to show what the building's going to do to the environment, the watershed, and all this other stuff. So people have their own little, consulting firm to take care of that. And also industries such as like Apple, and I've seen one. I think it's Google. No, it's Amazon that's doing it. They're who's called the sustainability director is on that commercial, and they're talking about how they're trying to switch over to electric vehicles and stuff like that, so they can be what's called carbon neutral. And that's what his job is just to be, make sure that Amazon is acting in an environmentally conscious way. So there's a lot of different crazy jobs out there. The potential to be a marine biologist, of course, climatologist, fish and game warden, everything. I have this one buddy he's an environmental toxicologist, I guess he would be. All right, but he works for the Department of not forestry, maybe it's, well, I don't know what department. It's one of the natural things in Pennsylvania. But his job is to just go back out into the woods in the Cook's Forest and stuff and go take some samples of the water and look for critters and stuff like that. And he loves it because he gets to go outside all the time. But he really hates it because at the end of the month he has to go back to the office and write all those reports. But he really enjoys the freedom to be able to, see what's happening out in Mother Nature. So there's a lot of jobs. And even if you're just being an accountant or a finance guy or a nurse, environmental science does end up in your field somehow, believe it or not. It's all connected, which we're going to talk about here in a little bit. So the Earth is an island in itself. It's an amazing thing. On this Earth, we have what's called the environment, which consists of all living and non-living things. All right, so it's all the minerals, rocks, and bugs and animals in one defined area. And the Earth is one defined area, but you can also take the environment of just here in Pittsburgh and put all the rivers and triangles and city in there, or you can just take the little environment of Moon Township. And believe it or not, the climate's a little bit different between those two. All right. Environmental science in this class is defined as the study of the natural world, how the natural world works, and how the environment affects humanity, us as humans, and how we affect it. So we look at environmental science and we say, hey, this is, we'll go through the scientific method and stuff in a little bit. But we say, hey, this is the science behind everything. This is how gravity works. This is how evaporation works, all this stuff. So you have a basis of science. And then we look and see how that basis of science affects our body. So if there's too much lead in the water, we know how much, it's going to make us go batty. So we try to keep that lead out of the water, right? And also how we affect it too. And what we're trying to do here with climate change is how we're affecting what's called the carbon cycle, which we'll talk about in PowerPoint 2. That we're actually releasing a lot of carbon. We're setting this natural cycle, what's called the carbon cycle, out of whack. We're putting way too much carbon into the atmosphere. Well, more carbon that's usually in there, right? Of how we grow up in humanity. And we're affecting that even though we don't really see it, but we can feel it, okay? And my definition of environmental science is just simply the study of the environment and humanity's ecological niches in it, how we affect the environment. So we rely on natural resources, and humans rely on natural resources. The natural resources are the substance and energy that we take from the environment and rely upon to survive. And that's all our food, our minerals, our fossil fuels, our trees. And I have human labor here in red, right? Because believe it or not, we need our human labor to be able to survive. Okay, we need to go out and be able to plant all these crops, right? And put these solar panels in. And, the reason that's in red is because that we usually didn't add that in there until we started becoming a civilization. Nation and started doing specialization. We didn't have to go out and everybody had to plant their food and gather hunters. We were able to start specializing so someone could be specialized as being the baker or the candlestick maker or the auto parts guy, right? So human labor is actually a natural resource out there. Now, renewable natural resources are replenished over a short period of time. And technically, when you look at the textbook definitions, it's usually typically a lifetime of an individual, like about 100 years per se. All right, because in each renewable energy is a little bit different. So a tree will take 80 to 100 years to get to its full potential, while a blade of grass only takes 30 days or whatever. Okay, or bamboo. Okay, so there's different renewable energies out there. But typically they renew themselves so we can use them again. Sunlight, wind, and wave energies are thought as perpetually renewed and are considered inexhaustible. But in actuality, in the laws of physics, which we'll learn here in a little bit, that nothing is inexhaustible. Even the sun is going to run out of energy in the middle, and there will be no more sunlight. And when the sunlight leaves us, so will the wind, and so will the wave energy. So it's not necessarily, good thing that's in a billion years, so we don't have to worry about it. So we think it's inexhaustible. But then we also have the renewables, such as the timber and water and animal populations and fertile soil, where we have to, um, maintain them. We have to manage them properly so they don't become exhaustible, okay, or become unusable. So just like the story of the Lorax, we got to remember that when we cut down a tree, we got to give it time to grow back so we can use it again. Non-renewable resources, on the other hand, are natural resources formed much slower than we use them, and are no longer available once we deplete them. So the coal, the natural gas, and the oil that we use out there in the world actually, took about 1,000,000 years to actually form. It took a long, long time for us to get to where we're at. And we take them out, and as soon as you burn that piece of coal, we're not going to get them back. I mean, it just dissipates and goes up into smoke, right? It's just a bunch of ash and smoke out there in the atmosphere. Having said that, just like how the sun will, in 1,000,000 years, someday lose all of its energy, coal in 1,000,000 years could reform itself. All right, that coal that you actually burn someday can go up into the atmosphere, and then another tree can take that carbon dioxide molecule that you released a long time ago, put it back in its trunk, and it can fall back over in a swamp, and then gets covered back over, and in 1,000,000 years get tossed around in the earth, and next thing you know, you have a coal. Okay, so even non-renewable energies are renewable. It just takes 1,000,000 years. So we rely on ecosystems for a lot of ecosystem services, for a lot of different things. We kind of take them for granted, all right? So in addition to the goods provided as resources, the oil, the natural gas, the water to drink, and the air to breathe, the environment also provides what's called an ecosystem service, such as the air and water purification. All right, so if it wasn't for the trees breathing in that carbon dioxide and putting that carbon in the trunk and releasing that oxygen, we might not have enough oxygen to breathe. That's an ecological service. All right. On my farm, I live on a farm, and we have what's called well water. And so the rain runs into the ground and percolates through the ground and ends up in what's called an aquifer. We'll learn about in water section of this class, and an aquifer on the bottom, and then I'm able to suck it out with a straw. But as it goes and trickles down throughout the ground, it is getting cleaned and purified. Right? Is also the natural recycling of nutrients, the climate regulation, the pollination. Just think of the bees. We had to go around and pollinate all those apple trees. What a pain in the butt would that would be. All right? And the waste recycling. All of our poop out there. If it wasn't for the anaerobic bacteria and all those other animals eating all those dead things, we'd be in trouble. All right? Population growth has amplified our impact on the environment. Right? Environmental science is the study of the environment and humanity's place in it, its ecological niche in it. And human population has grown exponentially. Okay? You see here's the graph of the human population. It's just huge. And you're going to have to read the first time, or watch, I guess, the first video I have for you, or first homework assignment is the most important video you ever see. And this is what it's talking about. It's talking about the exponential function in this J curve showing up. And this is when I see J curve show up, it means it's a red flag to me. Doesn't mean that it's good or it's bad. It's just I got to stop and pay attention. All right. And having said that, like I say, it's not good or bad because I love seeing a J curve in my market portfolio. Right, my Tesla stock that I have is going like this. It is insane. But do I think that's going to hang on? No. I mean, I hope it does. Right. But for it to explode like that, you kind of have to realize that it's got to come back down sometime. And same thing with human population. I'm not saying that the human population is going to crash. I just wanted to go over to S curve. That's why I want Tesla to do. I just want to get up here and just turn over to a little S curve and stay there for a while, and then sooner or later go back up. All right. But these J curves you got to really watch, and that's what that movie's all about. And I'm so glad that I have assigned this for a long time, because the COVID thing's exactly like that. The transportation of a virus around the world. So the human population really started after the agricultural revolution, when people began to grow their own crops and domesticate animals. We were able to settle down, and we had a little bit more food security during that time, and that has allowed us to be able to grow our population. And then the Industrial Revolution came on, which shifted life towards the urban city, and we started using fossil fuels, and that's right here, right? And I'm grateful for the Industrial Revolution. It really helped out. The use of fossil fuels has given us so much extra power and energy to use, all right? Better medicine, all right? If we didn't have the Industrial Revolution, I'd probably be dead right now, because I had a tree fall on me a long time ago, and I can hardly walk. Right, and just being able to walk is just amazing. But I couldn't do it without the medical advances. I mean, I have a back made of steel. I have titanium in my back. It's an amazing thing. So the Industrial Revolution was a great advantage, because people started living a lot longer, and actually were able to, the children were able to live to, instead of dying at the age of 3, and our population just totally exploded. But now we're up here with 7.6 billion people, I think, on the earth, and we've got to make the decision of how many people we can actually. It's called carrying capacity, which we'll learn here in a little bit. Does the earth have enough resources, renewable and non-renewable resources, to be able to feed everybody, and everybody drive cars and have a cell phone and all that other rigmarole? So when we look at human population, we have to look at our resource consumption. And that exerts a lot of social and economic and environmental pressures on the earth. And what we do in in environmental science, and I was about to say ecological economics, which is kind of like my forte. I like to call myself an ecological economist, is we calculate what is called the ecological footprint. All right. So I think this is let's just watch this video. I don't know if I have this. There's a video. We won't watch this video. I'll explain it. But go back to the PowerPoint and watch this video of ecological footprint. These are the guys that actually made it. All right. And it is simply just the measure of the ecological footprint is a cumulative area of land and water needed to provide resources and waste disposal for a typical person. So here's this is my ecological footprint. Every morning I get up, I get a little bit of corn from my cornflakes, all right, a little milk from the cow, all right, a little coffee from the Columbia, all right. I didn't use any wood products this morning, but I had a little fire last night, all right. Also, all the carbon that I've had to burn to heat my house and everything else. Okay, so all these things are added up into this little ecological footprint. Okay, and what we have found over the time is when we take all the biocapacity of the earth, which is, in other words, just another carrying capacity of the earth. All right. So we have all those earth in there, and we take this little calculation of take everybody else, 7.6 billion people out of this, and say, okay, yeah, for people to live, they really need about 2,500 calories to enough food. They need a gallon of water. They need so much wool to keep themselves warm and their clothes and all that other stuff. We add all that up, and right here is what's called the break-even point, right, of carrying capacity. So this one is the carrying capacity. And what we have found is that we're in what's called overshoot. And we're right here. So we are actually using this much more Earth's resources than the Earth can actually maintain. All right? So humans are using about 68% more resources than the Earth can replenish for us. Okay? And what we want to try to do is break even, right? We want to have just enough to get by. Okay? And we're not at that point right now. We want to be at this line or under this line, okay, for us to be able to live sustainable. Because you know, if you keep on using 30% more of your income, that is not too sustainable, is it? You're going to be in trouble. And that is called overshoot. Okay? There's natural capital, right? We're using more of the Earth's natural capital than the Earth can reinvest for us, okay? And Earth's natural capital is stored in the resources and ecosystems, and it's like a bank account, okay? We keep on taking it. Like that coal and that oil and that natural gas are like a little savings account that we have. And we are not able to make enough income to put that savings back into that bank account. All right, and we're going to be beat, so we got to make sure that we try to maintain that as long as we can. And just like a bank account, so if you leave the principal of your money intact and only spend the interest, the account remains full. But if you deplete the principal, the account will be drawn down and it will be exhausted. And that's what we're actually doing. We're pulling out 30% more of our principal than can be re-upped every single year. So we're definitely in trouble, and it's definitely not sustainable. Okay? So we need to do something about that. And historians have always inferred that the environmental degradation has contributed to the collapse of societies. Right? The Greeks and the Romans and the Angers. I mean, this is just a common theme throughout society of how we have actually collapsed. All right? And there's a good book by, I think his name is Jared Diamond, who wrote a book called Collapse. And he goes through a couple different civilizations that has actually collapsed over the eons because of environmental degradation, some other things too. All right, it's not always just an environment destroys it. Okay, it is also some other underlying things, but that's always a common thread with inside a failing society, to say. Okay, so today's society is globalist, meaning that it's similar, meaning a similar collapse could affect the whole entire world. All right, when we talk about climate change and all that stuff, we're all interlinked. All right, we trade with everybody nowadays. There's very few countries that we don't trade with. All right, and there was a famous book called The Limits to Growth that was written, I think it came out in 68 or 69. And it was pivotal moment of discussing this overshoot. All right, it was the first supercomputer out there that calculated the amount of people on Earth and put in all those little variables, how much we need to eat, drink, clothe ourselves. Started doing the ecological footprint for everybody to live sustainable and a happy, a decent life. All right, and what we have found is that right then, in 1968, when we were about to be in the overshoot, and we have not stopped. It was when we broke over that little area, and we haven't stopped consuming since. Right? Our current consumption and growth rates are definitely unsustainable. There's no ands, ifs, or buts about it. So we need to do something about that. And hopefully, we'll be able to do something about it. We still can live a good life. All right. But we'll talk about that a little bit further in this class. So environmental science is one of the reasons I love environmental science. Not only is it a study of environment, Mother Nature, that I love, and then human impact on it, because I like sociology and how people interact with things. All right, but environmental science is an interdisciplinary science, meaning it brings techniques and research from all these different disciplines. Because I like to call myself an ecological economist, but actually, I'm a jack of all trades, master of none. Right? And environmental science fits right into my little forte there. Right? Because you need to know not just exactly what ecology is, just a little bit about ecology, and a little bit about biology, and a little bit about chemistry and atmospheric science. And you got all the way around, all the way to political science, to engineering, to economics, to ethics. All these things come in realm with environmental science. So there's not one specialty when it comes to environmental science, but there is a lot of information being put together, and everything's interactive. All right, take for exactly. Let's look at this. Let's look at anthropology. Okay, that sometimes there's groups of individuals that have been doing things for thousands and thousands of years. So We used to do a lot of whaling way back when, and now everybody, I hope you know that most of the whaling, not every country, but it's illegal for us to have those big whaling ships to go out there anymore. Okay, but there is a group of Inuit Indians up there in Alaska and Canada area that have been whaling for thousands and thousands, I mean, not thousands of years, say hundreds of years. It's part of their culture. That's the way they live. Okay, so we've made that exemption for them to be able to live their life the way they want to. Because when they do their whaling, they use every single bit of that whale in their lifestyle. No part of that whale is ever wasted. Okay, and I say, hey, if you want to be in any way in it, you really want to go whaling, you can go ahead and whale just like the Inuit Indians. Okay, you can go grab a kayak in the dead of winter up there in Alaska, get in that icy cold water and go harpoon yourself. Throw a freaking harpoon at a whale. I mean, good luck with that. All right, but we allow them to do it because that's part of their culture. Okay, so we got to live a little bit. Okay. Environmental science and also involves not only looking at other people and how they live, because there's not one right way to live, but it's really based in scientific study of the environment and the interaction in our interactions with it. All right. So environmental science is that study, that scientific study in our interactions. Environmentalism is a little bit different. That's more of a social movement that's dedicated to protecting the natural world from undesirable changes and brought by human action. So environmentalism is going out and doing an environmental march, all right, and trying to get the government to change a little bit of some of our actions in the world, all right, and that's okay. That's you're allowed to be an environmentalist, but it's not the same as environmental science, okay? And we'll talk a little bit about how you can get active if you wanted to into this lecture. So science is a systematic process for learning about the world and testing and understanding about it. So it's systematic. It's a laid out plan that we have, and we can figure things out. Okay, and it needs to fall in a couple of different categories. So science may also refer to the cumulative body of knowledge that has arisen. All right, so it could be all of the science out there, as well as just someone coming up with a new scientific revelation, right? There's what's called descriptive science, which involves researching organisms, materials, and systems that are new or not well known, all right? So we're trying to figure out what's making these things tick, all right? And there's also what's called hypothesis-driven science, which experiments to test hypotheses as part of the scientific method, all right? So descriptive science trying to figure things out, hypothesis test things, okay? So a scientific method is a traditional approach to research. And for the test, you're going to have to know the scientific method, all right? And list it out. So scientific method is very, I probably learned this in the 5th grade. I know my kids did. Is a formalized technique of testing ideas. First, a scientist observes a phenomenon. You look, hey, that apple keeps on falling from the tree, and you question, why does that fall from the tree? All right. Then you form a hypothesis. Maybe something's pulling on that apple to make it drop to the ground. Okay. And you predict what to find. You test it, and you get your results. Okay. If the results fail to don't fall inside your required hypothesis, you got to go back and figure out what happened and test it again. All right. So in each experiment, you have 2 variables. You have what's called the independent variable, which is the condition that changes and is to be tested, and you have the dependent variables. That is, there is resulting condition that depends on the independent variable. So the independent variable is the ones that change and is to be tested. So the independent variable. So the dependent variable is the resulting conditions that depend on the variable. So the independent variable would be in like climate change would be temperature. Okay, is a function of all these different independent variables. Okay, how much carbon we have in the atmosphere, what cycle we are in, whether it's summer, winter, fall, spring. All right, how much cloud cover we have, how much whiteness is around to reflect the light, right? Or blackness if we're in the heat island effect. Okay, so all these different things. So dependent variable on that on the left hand side. I think I said that right. Left hand side will be temperature, and then the independent variables will be all those other ones, and how these independent variables affect the dependent variable. So in a controlled experiment, there's only one independent variable that has changed, the treatment part of the experiment which receives the change. And the controlled does not receive the change and serves as a point of comparison. Okay, so this is mostly done in the medical field. If you ever go, further on in life, maybe you'll do one of these. But just basically, like giving somebody a placebo and someone a not placebo. So the control group doesn't receive any change. They just get the fake drug, and the treatment group gets the drug. Okay, and then they see if there's any difference, if something actually affected that drug. Scientists record data and information in their studies. So quantitative data, which are expressed in numbers, are especially valued because numbers are easy to compare. So an experiment may disprove or fail to disprove the hypothesis, but it never proves to be true because there's always a chance that something is not right out there. So if enough evidence accumulates to support the hypothesis, the scientists will eventually conclude that it's well supported. So, everybody talks about scientific theory. Oh, it's just a theory that, here conspiracy theory, it can't really be true or whatever. But really what's happened with a scientific theory is that it is based on repeated observations. The repeated observation of that apple always falling down to the ground, right? Now, maybe someday that apple will not fall. Okay, that is a possibility in the world. Okay, we can lose all of our gravity. But as for now, we are 99.999% chance that apple is going to fall down from the ground. Okay, so we never claim pure proof in the scientific method. Okay, in a manipulated experiment, let's go back to this one. Well, first, the good thing about this quantitative data is just we're always adding up the numbers. All right, so it's just usually back data. All right, so if you're going to figure out, let's think here, a stock price, all right, or maybe the future rate of return of an investment, you go back and see how it's moved over time. All right, that's quantitative data. When I did my dissertation, I did it on what's called a community-supported agricultural system, which is a way of doing business for a farm. And when I got my data, I surveyed everybody, and they gave me all the answers, and I put it into my little model. Okay. There's also what's called a manipulative experiment, where the researcher actively chooses and manipulates the independent variable, which would be just like the placebo and the regular drug. And there's also what's called natural experiments, which compare how different variables are expressed in naturally occurring but differently context. So an independent variable varies naturally, and scientists search for correlations or statistical associations between these variables. So scientists use a lot of graphs and data to visually represent things, and graphs will always help to make patterns and trends in data visually apparent and easy to understand. So here are some 4 graphs that you might see throughout the book. We got a basic little line graph. All right, you see here you got the X and the Y axis. All right, and this is dry weight in time, and this is time of weeks. So how the algae grows after adding fertilizer. That's what it's actually telling us, and this is just represented in a line. So the unfertilized pond gets no algae growth, All right. We added fertilizer to the other one, right? The controlled and then independent variable. I added fertilizer to here, and you can see how the algae grew real fast. All right. This is the same information set in the bar chart. Okay. And it's the same information in what's called a scatter plot, and this is the same information in a little pie chart. Okay, so each one is representing the same kind of thing, but it just visually shown a little bit differently. So a scientific process continues beyond the scientific method. So when a researcher work is completed, it's submitted to what's called a journal. And the journal's editors ask several other scientists to do what's called peer review of the work, meaning that they provide the comments and criticisms to judge whether or not it merits publication. So they check the data, make sure the math is right, all this other rigmarole. And further peer review takes place even after that. Okay. As scientists apply for grants and funding to present their research at the conference presentation. So other scientists may attempt to repeat this experiment. So, I did my dissertation and I wrote it all up and, did my survey and did my econometric model and all this other stuff. And I had my peers review it and say, okay, this is really good. And then I put it out there, got it published. And I still don't know if what's called I did a pricing model. So I still don't know if my pricing model is valid because no one's ever tried to repeat the same experiment I've done. Maybe they have, I just don't know it. All right, but I doubt it. So, I can't really say I have a confidence level about at the end of that about 76%. That my model represented about 76% of the price of a community share of a community-supported agriculture program. And, that was pretty good data for me, but I hope that someone can repeat it. All right. It's not really solid data to repeat it. We can keep on repeating that apple falling from the tree. We can keep on repeating that if we add more carbon dioxide to a closed atmosphere like our Earth or a little greenhouse, is going to get warmer. Okay, we can figure that out. We have a mathematical equation for that because it's repeatable all over the time. All right. So when it comes to the scientific method, everybody's used to just seeing these 5 little steps with the observation, question, hypothesis, prediction, test, and results. Right. But on the test, we are going to need to know this whole thing, and I just add in peer review. So if we're not getting peer review and having our people look over our stuff, and if we're not sharing it and saying, hey, give me your honest feedback, it's not really scientific information. Okay, and I've seen a lot of people put some stuff out there in the world and say, hey, this isn't scientific information. This is a bunch of hubbub. All right, or they don't give you all the data. So make sure when you see a paper out there talking about something, they are able to share their data and tell you how they got to that situation, and they're also saying, hey, here's all this stuff. You go repeat it too. See if you can get the same result. I'm interested if you can, because I would love to see if someone gets another pricing model that did another pricing model of CSA and they got the same results that I got. All right, I would love to see that. Please, someone do that. Okay. So if a hypothesis survives repeated testing over and over and over and over again and consistently predicts experimental outcomes accurately, it may incorporate it into finally the scientific theory. So a scientific theory isn't just a harebrained conspiracy theory. A scientific theory is repeated over and over and over and over and over again. All right, even you too can repeat the same experiment. Okay. A theory is widely accepted and well-tested explanation of one or more cause and effect relationships that have been extensively evaluated by a great amount of testing. All right, theories are such as evolution, cell theory, atomic theory, plate tectonics, consolidated many related hypotheses over time. So science is always building, always becoming more refined over time as we increase our knowledge of the world. So periodically, science will undergo a monumental shift where one paradigm or dominant view is replaced with another. This doesn't happen too often, but it does happen from time to time. Okay. Prior to the Copernicus, right? We all thought that the Earth was the center of the universe. Okay. Too bad it was only Copernicus this time, because a lot of the ancients knew that we weren't the center of the universe. But that's the paramount shift that we're kind of thinking about. Addressing environmental issues requires us not to only understand science, but also how to use it to solve our problems. And, we're understanding more and more about climate change, and it's going to take a paradigm shift in our social thinking to really solve this problem. Okay? Where was I here? So environmental ethics, right? And it really comes down to climate change, comes down to an ethics kind of thought, right? So ethics is a branch of philosophy that studies how people decide what is good and bad and right and wrong. And, there is no one right way to live, in my opinion. Okay, you want to be who you want to be. But we do have some kind of golden rules as a society. Um, be good to other people, right? That's kind of one of those good, right? One of those golden rules that's in every single religion. Even you don't even have to be religious to know that you should be nice to individuals, right? So we kind of know that good and the bad, right? But there's some very tricky things in environmental science is that people need to have jobs, right? But the bad thing is some of those jobs are polluting the earth. And how can we find that middle ground so we can still have people working, we can still run our cars, but we're not actually polluting the earth all over the place, okay? And that's like the middle ground, and each one's ethics is kind of, it's a little bit more gray in those areas. It's not as black and white as do unto others as you would have to do unto you. All right. So ethical standards are criteria that helps make this distinction. So categorical imperatives advise us to treat others as you would prefer to be treated. That's categorical imperative. All right. But the principle of utility holds that something is right when it produces the greatest practical benefit for most people. All right. And that's, the social cost equals the social benefit. All right. They also it's also called the Pareto criteria, where no one is worse off and no one is better off. All right. No one is worse off by driving that car, and no one is better off by driving that car. So relatives believe that the ethics vary with social context, while universal believes that ethics are consistent across all cultures and contexts. I mean, kind of both of these people. All right, so I think it's universal that you do unto others as you would have done unto you. I think that's universal. But there's different different other people that believe in, per se, more than one wife. All right, polygamy or whatever. Okay. I might not believe in that. Some other people might believe in that, and I gotta let them be who they want to be because this is America. Or I guess you can't have polygamy in America or wherever in the world, right? Yeah, Saudi Arabia, maybe they have it there. I don't know where they have it, but you can understand what I'm saying. Everybody is allowed to be the culture they want to be. Okay, as long as they're being nice to me. The application of ethical standards is in relationship between humans and non-human entities in its environment. So, as a present generation, we're obliged are we obliged to conserve resources? That's a question. That is not, a statement from me. Should we save enough oil for the next generations to go, or should we just try to innovate into something else instead of using that fossil fuels? Come up with another idea that they can run their cars on. Okay. Can we justify some communities being more polluted? All right. We have to put our nuclear waste somewhere. Is that okay if we put it in Yucca Mountain and keep Pennsylvania nice and clean of that nuclear waste? Are humans justified from driving from some species to extinction? All right. We got rid of the saber-toothed tiger because it was too dangerous out there for us. Okay. Were we justified of doing that? The answer to these questions depend on, of course, ethical standards adopted by the person and the breadth of the person's domain of ethical concerns. And domains of concerns in relationship to the national order divide into three ethical perspectives. All right. The first one is anthropocentrism. All right. which is a human-centered view that evaluates costs and benefits of action solely on the impact of the people. So it's just on humanity. All right, is humanity going to prosper? Then there's biocentrism, which adds in the rest of the life. All right, adds in the birds and the fish and the grass and the mushrooms and the tigers and the bears and everything else. And then there's ecocentrism, which takes in everything. All right, judges action based on the effects of ecological systems. Okay, so humans, we're just centered on human life. We want to be able to drive our cars, so we'll just keep on getting that oil out of there and putting it into our gas, into our cars. All right, but we want to save the animals too, right? So we will do what's called a land bridge and have those animals have a nice little bridge that they can walk across so they don't have to go across the busy highway. So we'll create a little path for them to go over top the highway and get back and forth and do their wandering and meandering around and not have to cross the busy highway. All right, so that will be a biocentric. Then there's ecocentrism, but what are we going to do about the climate change, right? All that carbon, excess carbon we're adding to the atmosphere. That doesn't seem like something right, all right? So that's taken into consideration the whole world, okay? And you can be whoever you want to be. I'm probably in between all three of these things, I would assume, okay? But I'm more of a holistic perspective, the whole thing, okay? In America, conservation and preservation arose about the 20th century. That's when we really started conserving the Grand. You can see good old Teddy over here, Teddy Roosevelt. That's when we started actually having the Grand Canyon as a national park and stuff like that. So biocentric and ecocentric worldviews increased during the Industrial Revolution as we started putting out more pollution into the atmosphere. All right. Two of the people that did that, one guy was John Muir, promoted preserving ethics, believing that the environment should be protected and pristine and in its unaltered state. All right, and he worked with Teddy Roosevelt to increase the national parks that we have around the United States. Gifford Pinchot promoted conservation ethics, which hold people should put natural resources to use, but have a responsibility to use them wisely. All right, we shifted over to this kind of thinking, and this is kind of my thinking too. We'll never really get rid of fossil fuels, folks. I mean, as much as I would love to not do any more fracking, it's almost impossible not to. All right, but we can do these things in a responsible way and not hurt the environment and not use them too quickly as well. So the future generations can have something to heat their homes with as well. Then along came out Aldo Leopold, which was the original forest manager who embraced the government's policy of shooting predators to increase population of deer and other game. So he said, hey, let's go around there and shoot all those wolves and we'll be able to have other game out there. But then over time, he took more of an ecocentric view. All right, he realized that getting rid of these top predators in the food chain was not a very good idea. All right, so it came back to more of a ecocentric view. And most of the big thinkers of today, and even the ones of the past, started moving into this ecocentric view because we're realizing this more and more with climate change affecting the way we have, or the way we are. There's also what's called environmental justice, and this is also an ethical kind of thing. All right, and environmental justice involves the fair and equitable treatment of all people in respect to the environment, policies and practices in regards to their income, race, and ethnicity. Okay, and when we look around the world, we see that poor people and ethnic minorities tend to be exposed to more pollution, hazards, and environmental degradation than the wealthier. All right, it's the poor people that actually have the nuclear waste in their backyard, or we have these places in America which we call cancer alleys, which are downwind from some big, huge oil refinery or a factory or something like that, and their cancer rate is a little bit higher. And since those houses are a little bit cheaper, Mostly they're full of the poor communities. And then upwind, that doesn't get that wind, that's where we see the wealthier people living. So there's definitely a big disparity between those two situations. And environmental justice tries to address those kind of things. So we have science that bases our knowledge, and then we have our ethics that affect how we apply that science. And then the justice is how we apply that science in equality. Okay, so everybody gets to have clean air, clean water, and a healthy place to live. All right, and you can see these different areas. What are the health, environmental risks to our farm workers out there? All right, bending over. All not only is the body getting hurt, but they also have um, subject to pesticides and things like that. You can see the children in New Orleans after Hurricane Katrina. All right, we've got a lot of kids in Mississippi getting what's called ringworm in their feet, which is due to plain and sewage. All right, and you usually don't see that unless you're in a third world country, but it's happening here in America as well. And of course, you can see that big power plant and the house right in front of the power plant, or in the back of the power plant, or whatever. The power plant's in their backyard. And you'll see that most of the communities around these kind of facilities are a little bit less well off than the wealthier communities. So sustainability in our future. So sustainability is, let me see how much we got left here. So I don't want to get too, we're almost done, okay. Sustainability and, sorry about that, folks. Sustainability is the guiding principle of modern environmental science, right? And it is my guiding principle, and it's a concept you will encounter throughout this course. All right, you're not going to hear too many people in the mainstream media talk about sustainability, but you're going to hear me talk about it a lot. All right, and it just means that we're living within our prime means. We are keeping within inside of our ecological footprint, the carrying capacity of the earth. All right, that we're conserving Earth's resources so that the people in the future can have some and be able to meet their needs. They'll still be able to drive a car per se, or have enough food and enough shelter. And it's also maintaining fully functional ecosystems. Okay, making sure that we have those services available for us in the future. So the environmental impact that humans have grown due to a combination of human population excessive. So about 200,000 people are added to the planet daily. And the 20 wealthiest nations have about 5 times per capita income than the poorest. And we see this little ecological footprints of different nations. So you see the United States. They use about 8.6 hectares, and each hectare is about 2.5 acres of a land available each day, all right, to live our lives. So the average American uses about, so that would be 16 acres, let's say. 16 acres of productive land to grow our food, to mine our metals, to drink our water, to drive our cars, all that stuff. Okay, and here you got the world average at only 2.9 acres, so that'd be 8 acres. Okay, unbelievable. Okay, so much more. It's said that the United States has 25% of the world's population, and we consume 25% of the world's resources. 5% of the population consume 25% of the world's resources. And we need to make the decision whether or not that's ethical and if that's environmentally justified. Okay? Because we have 5% of the population. We have 330 million, somewhere around 328 million people in the United States. China has over 1 billion. So you can imagine if a billion more people, they have 1.3 billion, we have 300 million. If 1 billion people more try to live like the United States. Remember that ecological overshoot we saw before? We were already, at 68%. Add another billion people living like us. What would that overshoot look like then? It's not going to happen. It's not going to happen. Okay? So the energy choices we we choose will shape our future. So our reliance on fossil fuels is one of the best examples of how resource consumption amplifies the environmental impact. Fossil fuels allowed us to power all this machinery, industrial revolution, grow all these crops, and run our vehicles, and have a great transportation network, all these great things. But fossil fuels are non-renewable. They're going to run out. They generate a lot of pollution. They have disrupted the ecosystems, and they are, it's just craziness. And we need to have a paramount shift of how we're extracting this stuff and actually using it, and the amount of consumption that we're using. But sustainable solutions abound. They're all over the place. That's what I love about this field of study, is that we do have plenty of solutions. All right, renewable energy sources are replacing fossil fuels. Soil conservation and the way we plant our crops, believe it or not, are a lot better today than they were years and years and years ago. Our technology is becoming more efficient. We got now laws that help us so we're not putting this poison all over the place anymore for these companies. We're identifying nature habitats and preserving species from going extinct, and we're doing better waste management. So there's a lot of sustainable solutions, and you as a student can help out too. There's a lot of student programs that are promoted around campuses. Okay, and even here on Robert Morris, such as recycling programs out there. All right, this one's collecting some electronic waste. Okay, so there's a lot of campuses out there, or you can just get active like me. I'm a professor, but I go out and every year we didn't go on this year because of COVID. I don't think we even had it, but and I think it was 2 years ago this came up. It was in March, September 20th. Here's my family out there, and we went down for the climate march. Right there I am. We went down and talked to all the senators, and guess what? I got stuck in the elevator with my favorite senator, Bernie Sanders, baby. I'm still heartbroken he's not going to be president. But I got to meet him because we went around, we lobbied all the senators, and we said, hey, we got to do something about climate change. And these kids right here are actually the DAPL kids. I don't know if you guys know about No DAPL or the Exxon. This, like 2 years ago, a lot of people camped out, and the Indians said, hey, you're not going to put this pipeline through our reservation and all this stuff. Okay. But all these kids are them right there. That's my kid. Right? And they all met with Bernie Sanders to talk about their concerns. All right, so you can get active too. Okay, so with fewer than half of the students at most schools taking any kind of environmental science course, many students are lacking environmental literacy. It's a tough thing. All right, so hopefully by the time we're done with this class, you'll have some environmental literacy inside you. All right, you'll be able to gain better understanding how the world works and be prepared for the growth of green-collar jobs. I mean, we got such a great opportunity ahead of us when it comes to jobs, and the green-collar jobs to help our society navigate these challenging and creating a sustainable future. So you guys are the future. You are the way to be. Hopefully this class is going to give you some basic foundations that when you get into your trade, your workforce, you can start applying some of these things and making this world a little bit better. All right? So that is it for the first presentation, and I will download this to YouTube, and then we will get this going to Blackboard, and we'll see you guys on Thursday for the next one. Thanks. Bye-bye.